This is the 19th video in a series devoted to introductory proofwriting. In the last video, we looked at the basics of functions, including injective and surjective functions. And now we want to look at compositions of functions, inverse functions, and some other things. Okay, so let's get started. So let's say we're given functions f, which goes from a to b, and g, which goes from b to c. Then we can define a new function, which is called g composed with f, and this is the notation. And it goes from a to c, and it's defined as follows. So g composed with f of x is the same thing as g of f of x. So in other words, we apply the function f to x, and then that result is applied by the function g. So notice x is an element of a. When we plug it into f, we get an element of b. And then when we plug that into g, we get an element of c. So that's how this works. Here's also a nice diagram. So f is like an arrow going from a to b. G is like an arrow going from B to C, and then the composition is like your shortcut. So it's an arrow from A all the way to C. Okay, let's look at a really basic example that comes from like the definition of a function as a subset of the cross product. So let's consider the set A, which has lowercase a, b, c, d. The set B, which has the numbers 1, 2, 3, 4, 5, and the set C, which has W, X, Y, and Z. And then we'll define a function f. Notice that under this setup, f goes from A to B, and it's the following ordered pairs. So A, 3, B, 2, C, 1, and D, 3. And then we've got a function g, and notice that by the way we have this set up, it's a function from b to c. So it has 1w, 2x, 3z, 4z, and then 5w. Okay, and now we'd like to write the composition as a set. So let's get to it. So let's say we have our set A here, so we can put it out as a diagram as these points A, B, C, and D. Then we have our set B here, which is like just the points 1, 2, 3, 4, 5. And then finally our set C, which is W, X, Y, and Z. Okay, and now maybe this blue arrow will be what F does to assign elements of A to elements of B. So notice it takes A to 3, so that gives us this sort of assignment here. It takes B to the number 2, so that would be that sort of arrow. It takes C to the number 1, so that would be an arrow like that. And then finally it takes D to 3. So let's notice it misses 4 and 5, but that's totally okay. And then let's say in this magenta color, we'll outline the action of G. So G takes 1 to W, so that would be like an arrow right across. It takes 2 to X, 3 to Z, 4 also to Z, and then 5 up to Y. So it does that sort of action. And now let's take this and write down G composed with F as a set. So hopefully this shouldn't be too bad. Maybe we'll cut out the middle on these in green and trace what happens to the elements of A, B, and C. So notice that this element of A goes to 3 and then all the way down to Z. So what that tells us is that G composed with F of A is Z, which means we have the ordered pair A, Z in this set. Okay. Now what about B? So B is going to loop up here through 2 and then straight across to Z. So we start at B, we end at X. Sorry, I should have said X. So that tells us the ordered pair B, X is an element of our function. Okay, then what about C? Well, C loops up here to 1 and then straight across to W. So that tells us that in the end, under this composition, C is sent to W. That gives us the ordered pair C, W in this composition. Then we have one more to check, and notice that takes d up to 3, but then 3 branches down back to z. So that means d gets sent to z in the end. So we have d comma z is our last ordered pair. And that would be a full set description of this composition of functions. Okay, so now let's do some more familiar examples. So our next example will involve some functions that are familiar from calculus class. So they're both functions of real numbers to real numbers. The first one, which we'll call f, sends x to x times e to the x. So let's notice that under the notation that we used last time, that would be equivalent to writing it as x gets mapped to x e to the x, and we could put an f up here, just to be familiar with all of the different notations of how to describe assignment. And then g takes x to x squared plus 3x. So we could write that as x gets sent to x squared plus 3x via the function g. And now since the domain and the codomain are the same, we can compose these in any order we want. So let's do that. So let's first calculate g composed with f. So that will be g of f of x, but that will be g with f of x inside, so that's x times e to the x. But g is telling us to square something, multiply it by 3, and then add those together. So that gives us x squared e to the 2x. That's what we get for squaring it. Of course, we're using standard exponential rules there. And then plus 3x e to the x. Okay, nice. And now let's do the composition in the other order. We have f composed with g of x. So that's f of g of x. So that'll be what? F evaluated at x squared plus 3x, but that ends up being x squared plus 3x times e to the x squared plus 3x. But I guess maybe the quickest takeaway here is that these are not equal. So notice that f composed with g and g composed with f are not equal to each other. And that is hopefully fairly familiar from like a calculus class. But what we get here is that the composition of functions is not commutative. Well, in fact, if we don't have the right sets chosen, then one direction doesn't even make any sense. Okay, another thing that I'll just state right now, but I won't prove, you can find the proof in the book of proof, which I'm using as a textbook for this course, is that the composition of functions is associative. The proof is pretty straightforward, and I don't think it's really illuminating in any way. So now let's move on to how injective and surjective functions behave under this composition. So for this theorem, we want to suppose that f is a function from a to b and g is a function from b to c, just like our setup over here for defining composition. Furthermore, we'll assume that they are both injective, and then we'll show that their composition is injective. But we'll also show that if they are both surjective, then their composition is also surjective. So this is really two proofs in one. So let's prove the injectivity proof. So let's suppose that f and g are injective, and that we have x and y in the domain of g composed with f, so that will be in A, such that when we apply g composed with f to x, we get the same thing as applying g composed with f to y. And what we'd like to do is see that this leads to having x equals y. Recall that that was our standard outline for proving something was injective. Okay, so let's see how we can do that. So notice that this tells us via the definition of composition that g of f of x is equal to g of f of y. But now we'll use the fact that g is injective to say that f of x is equal to f of y. Remember, that's the definition of injectivity. So let's write that down. So since g is injective, we have f of x equals f of y. Great. But now we'll just do the same thing with f. So now since f is injective, we have x equals y. But that's exactly all we needed to do to show that the composition was injective. So let's maybe look at our beginning step and our ending step. So we had an x and a y in A such that g of f of x was equal to g of f of y. And then we did a calculation, including using the fact that g and f were both injective, and we landed at x equals y. And recall that that was exactly the way to prove something was injective. Okay, so now let's flip this around and show the surjectivity statement is also true. So in other words, what we'd like to do is suppose that f and g are surjective, and somehow get that f composed with g, or g composed with f, I should say, is also surjective. But remember, that means we need to take something in the codomain of g composed with f and find a preimage for it. Okay, so let's do that. So let's suppose f and g are surjective, and little c is an element of capital C. So we need to take something from capital C because g composed with f goes from A to C. So our end game will be to find a lowercase a in A that gets mapped to C under this composition. Okay, so now let's apply the surjectivity of our component functions. Okay, so since g is surjective, we have some little b in B such that g of little b equals C. So that's exactly the definition of surjectivity applied to g, which we are assuming is surjective. And now we'll do that again, applying the definition of surjectivity of f. So since f is surjective, we have a little a in A such that f of little a is equal to b. And now we're essentially home free. We can just make the following observation, that g composed with f evaluated at this little a is exactly equal to g of f of a, but that's g of b. But remember that b was chosen just so that it gets mapped to C under g. So that's exactly what we needed to do. So what did we do? We took an arbitrary C in the codomain, and via the definition of surjectivity and the properties of the given functions, we found an A in the domain such that that A gets mapped to that C under our composition of functions. But that's exactly what we need in order for this composition to be surjective. Okay, so now that we've done this, let's look at inverse functions. So hand in hand with the notion of a composition of functions is the notion of an inverse function. So let's build up towards that definition. We'll need something called the identity function first. So given any set x, so that's a capital X, the identity function, which we'll write as I sub x, goes from x to x. And what does it do? Well, essentially it doesn't do anything. So it takes every element to itself. So this is a lowercase x here being mapped to itself. And that's true for all little x in x. Okay, that's cool. Then, given a bijective function f going from a to b, we say that this function g going from b to a is its inverse if two things are satisfied. G composed with f is the identity on a. So notice if we compose it in that order, we'll go from a to a. And then f composed with g is the identity on b. So if we compose it in that order, we go from b to b. And then I should point out here that under this setting, we have a special name for g, and that is the inverse of f. So we'll write it as f inverse like this. And there's a bit of stuff that we're skipping here, like how do we know that having a bijective function means that we have an inverse and stuff like that, but I think that's okay for now. Okay, so now let's look at the following example. So we've got f, which goes from the real numbers -1 to the real numbers -2. And it takes x to 2x plus 1 over x minus 1. So I won't check this as bijective. We checked that a function very similar to this was bijective earlier. So what we'll just do is find its inverse. And we're going to find its inverse using the standard like pre-calculus method. Okay, so let's set y equal to 2x plus 1 over x minus 1, and then we'll swap x and y, so that'll give us x equals 2y plus 1 over over y minus 1, and now we'll solve for y. So let's see, that's going to give us x times y minus x equals 2y plus 1. Now we'd like to gather all the y's on one side of the equation. That gives us xy minus 2y equals x plus 1. Now we can factor a y out of the left-hand side. That leaves us with y times the quantity x minus 2 equals x plus 1, which tells us that y equals x plus 1 over x minus 2. And then finally, that's what we assign to f inverse. So f inverse of x is equal to x plus 1 over x minus 2. And notice it has the correct domain and codomain. Its domain is definitely all real numbers except for 2, and then its codomain is definitely all real numbers except for 1. And in fact, that's its range as well. And then you can check here that if you compose f with f inverse, you get the identity function. So that's good. Let's look at another example. For our next example, we'll take the function g from z squared to z squared. So that's z cross z to itself. And we'll say that it takes an ordered pair m comma n to the ordered pair 2m plus n comma 5m plus 3n. We could do this by brute force, but I think we're going to assume that most people have seen linear algebra and use a trick here. It's not really much of a trick. So what we'll do is change our notation. And instead of writing these as ordered pairs, we'll write them as two-dimensional vectors. So that means we have g evaluated at the vector mn gives us the vector 2m plus n, 5m plus 3n. But this action over here looks exactly like multiplication by a 2 by 2 matrix. And what is that 2 by 2 matrix? Well, we can deconstruct it fairly easily. So this 2m plus n tells us that we should have a 2 here and a 1 here. And then this 5m plus 3n tells us we should have a 5 here and a 3 here. Now, if you want to, we can check that everything works, but as you'll see, it will work. And by check, I mean we're going to multiply this matrix that we found, 2, 1, 5, 3, into mn and make sure we get the right output. But let's see, swiveling this 2, 1 into mn gives us 2m plus n. Here using like standard matrix vector multiplication, then swiveling this 5, 3 into the mn gives us 5m plus 3n as needed. So this all checks out. So now in order to find the inverse of this function, all we have to do is find the inverse matrix. So let's do that. So we want 2, 1, 5, 3 inverse. So how do we do that? Well, it's 1 over the determinant. So 1 over AD minus BC. So 2 times 3 minus 5 times 1. And then we'll swap the diagonals, 3, 2. And then we'll negate the off diagonal. So -1, -5. So something like that. But now let's notice that this number right here is exactly 1 over 1, which is the number 1, which tells us that our inverse is simply this matrix 3, -1, -5, 2. And I actually chose those numbers nicely because if we had gotten a fraction here, then this would not have been bijective in the integers, and we would not have been able to invert this in the integers. So it's important that we got integer entries this whole way. Okay, so now we could like put this back into our original notation and say that gm inverse of mn is equal to, let's see, it'll be 3m minus n, comma, minus 5m plus 2n. Just putting everything back in order. And this will be the inverse. And now you can check that these are inverses, but I'll leave that to you. Okay, now we're gonna look at the notion of an image and a pre-image. So let's suppose we have a function f which goes from a set A to a set B. Then if we have a subset x of A, the image of x under A, but generally we don't write that if the context is known. So the image of X is, well, we'll denote it by F evaluated at the whole set. So we read that as F of X, or the image of X. So it's going to be everything of the form F of little x as X goes through all of capital X. Now let's quickly notice that the image of X is a subset of the codomain B. In fact, it's a subset of the range. Next, if we take Y to be an element of the codomain B, the preimage of Y, which we'll denote by F inverse of Y, or just say the words preimage of Y, it'll be the set of all X in A such that F of X is an element of Y. Now let's notice that F inverse of Y, or the preimage of Y, is a subset of A, so that's important. The image is a subset of the codomain, while as the preimage is a subset of the domain. Okay, let's look at an example. Let's say we've got the set A, which contains lowercase a, b, c, d, e, and a set B, which contains the numbers 1, 2, 3, 4, 5. And then our function f is defined by the following ordered pairs: a, 1, b, 3, c, 1, d, 4, and e, 2. So let's find the image of a certain set. So let's find the image of the set containing a, b, and c. So that'll be 1 because f of a is 1, and then 3 because f of b is 3, but then f of c is also 1, but we already have that listed, so that doesn't add to our set. Okay, that's cool. Now what about f of the whole set A? So this would be like the image of the entire function, or the range of the entire function. So let's work through A, B, C, D, and E. So A gets sent to 1, let's see, B gets sent to 3, D gets sent to 4, and E gets sent to 2. So in the end, we get 1, 2, 3, 4. So that's not quite the whole codomain, but that is the range because it's the image of the domain. Okay, so now what about the preimage of the set containing 1 and 2? So let's see what that'll leave us with. So we want to look for everything that gets mapped to 1. So A gets mapped to 1 and C also gets mapped to 1. So we get A, C. Those are the things that are mapped to 1. And then what is mapped to 2? Well, E is the only thing that's mapped to 2, so we get E. Okay, great. Now let's look at one more. Let's look at the preimage of the singleton 5. But let's notice that nothing gets mapped to the number 5, so this just gives us the empty set. Okay, let's look at another example. For our next example, let's consider the function g. It goes from r to r, and it's defined to be the sine function. Okay, so let's see what we have. Let's do the image of the following set. Let's say it's everything of the form n times pi over 2 as n runs through all integers. Okay, so what do we know about this? Well, if n is an even integer, then we get a multiple of pi. But sine of a multiple of pi is 0. So we know that this set contains the number 0. But then if n is equal to 1, we get pi over 2. But sine of pi over 2 is 1, so we're good to go there. Then if n is equal to -1, we get sine of negative pi over 2, but sine of negative pi over 2 is -1. So those will be the 3 numbers that we get. And I guess maybe you could argue that those are the only 3 numbers, but I think we'll leave it at that. Now let's look at the preimage of something. So let's take the preimage of the set containing the square root of 2 over 2 and negative the square root of 2 over 2. So let's notice that this will be everything of the form pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, so on and so forth. But let's notice that those are everything that is pi over 4 away from something that is n pi over 2. So we can actually write that set as follows. It's going to look like pi over 4 plus n times pi over 2 as n ranges through all integers. So we'll get something like that. Now we could do some other preimages as well if we wanted to. Like what if we did the preimage of the interval from 0 up to 1, maybe not including 0 but including 1. So this is a bit trickier, but notice that sine of 0 is 0, so we could include the point 0, or we'll start an interval at 0. And then sine of pi over 2 is 1, so this takes us up to pi over 2. So we'll have something like that. But then we'll union this with a bunch of other things that look fairly similar, and that's based off the periodicity of sine. So let's see, we'll union this with, maybe the next one will be 2 pi to 5 pi over 2. Notice that's 2 pi plus pi over 2. And then we'll get something back here as well, which is like negative 2 pi, and then negative 2 pi plus pi over 2, which I think is negative 3 pi over 2. So we get something of that form, and then we'll union those infinitely in both directions. But in fact, I think we could write that in the following setup. Maybe it would be the union as we work over all integers n of 2 times n times pi, and then 2 times n times pi plus pi over 2. I think that would be a nice way of writing that pre-image. And in fact, in order to make this a little bit more interesting, let's exchange this interval from 0 to 1 to the interval from 0 to infinity. And notice nothing changes. And that's because sine is never larger than 1. So adding all of those numbers larger than 1 doesn't allow you to get anything else out of the domain when taking this pre-image. So I'm going to end with the statement of a pretty important theorem, and we'll prove parts of it before leaving you with some warm-up. So the following is a classic theorem. We'll prove 2 parts of it, but it also makes for some really important classic exercises that are somewhat of a rite of passage when going through a class like this. So let's say we've got a function f from a to b. We have 2 subsets of a, which are w and x, 2 subsets of b, which are y and z, then the following 6 containments or equalities of sets hold. So the image of w intersect x is a subset of the image of w intersect the image of x. Then the image of the union of w and x is equal to the union of the images. Then next, x is a subset of the preimage of the image of x. So that's how you would read that properly. Then notice the preimage acts very nicely. In fact, the intersection and the union distribute with giving you equalities there. So in fact, with union and intersection, the preimage is almost more natural than the image. And then we also have this statement. The image of the preimage of y is a subset of y. Okay, so let's see which one of these we should do. So let's maybe do this one first, and then we'll do one more. So let's see, how do we want to do this? Well, with double set containment. So let's suppose that little x is an element of the preimage of y intersect z. But what does it mean to be in the preimage? Well, that means if you apply f to little x, you land in y intersect z. That's exactly what it means to be in the preimage. But what does it mean to be in the intersection? It means that you're in both of those sets. So f of x must be in y, and f of x must be an element of z as well. But where do we go from there? Well, if f of x is in y, that means that x is in the preimage of y. That's by the definition of the preimage. And then if f of x is in z, that means that x is in the preimage of z. So again, that's by the definition of the preimage. So what have we shown so far? We've shown that the preimage of y intersect z is a subset of the preimage of y intersected with the preimage of z. And what's left is to show the other containment. But I'm actually going to leave that as an exercise because it goes very, very similarly. Okay, let's do one more. So maybe for our next one, we'll prove this last statement here. So this is a single containment, so we only have to do one thing. So let's maybe suppose that little y is an element of the image of the preimage of y. Okay, so let's decompose this a little bit at a time. What does it mean to be in the image? Well, by the definition over here, that tells us that y equals f of little x for some little x in this inside set. But that inside set is inside f inverse of y, or the preimage of y. But what does it mean to be in the preimage of y? So being in the preimage of y means f of x is in y. Again, that's what it means to be in the preimage of y. But now we can just put these two equations together, so this equation and this equation, and we have it. So since f of x is equal to y, we have y is in y. But look at what we've done. We started here with y in the left-hand side, and we ended with y in the right-hand side, but that's exactly what it takes to prove this subset relationship. Okay, so now I've got some warm-ups for you. So here are 3 nice warm-up problems to practice what we've seen. So the first is to define 2 functions from integers to integers, which we'll call f and g by the following piecewise rules. So f of n is 2n minus 1 if n is bigger than or equal to 0, and 2n if n is less than 0. And then g of n is n plus 1 if n is even, and 3n if n is odd. And then you'd like to determine the composition of f with g and g with f. So I know at least one of these can be simplified quite a bit into something nice. So for the second one, let's define this function f from r to the open interval from 0 to infinity by f of x equals e to the x cubed plus 1. So let's show that f is bijective and find its inverse. Finally, we've got a counting problem. So we'd like to determine how many functions we have from the set a, b, c, d, e, f to the set 1, 2, 3, 4, 5, 6 with the property that the cardinality of the preimage of the singleton 5 is equal to 3. So that means there are 3 elements from the domain that get mapped to 5. And if you're not in the course that I'm teaching, then you might want to prove the rest of those statements from that theorem. If you are in the course that I'm teaching, well, you'll likely do those for part of your homework. And that's a good place to stop.